Hi guys, welcome to Learning Electronics Repair. I have a little switch mode power supply here. It's actually a battery charger from an electric drill, so the battery plugs over here. That's what charges the battery from these contacts. But really it's just a little switch mode power supply. Most likely will be constant current rather than constant voltage you would expect for a battery charger, but other than that it's just a switch mode. The guy who brought it in, Handy Andy from the local repair shop, phone repair shop that is, asked me if I could look at this for him today. So he says it's dead, it's not charging the batteries. So we can take a look at what we have here. This is the mains power coming in. This is a fuse, it says F1, 250 volts, 2 amps, so we know it's a fuse. We have, looks like an inductor coil here, a capacitor, 2 more inductors. So this is basically filtering. This prevents any noise from the switching transformer, the switching transistors getting back into the main supply, just preventing interference. These 2 coils are not a transformer, they're just 2 inductors, one in the live and one in the neutral. And then that comes to here. So these 4 diodes, this is the bridge rectifier. This will convert the 240 volts AC into DC and charge this capacitor. And normally this would charge to about 320 volts. You may wonder why from 240 volt mains. Well, the 240 volts, if you like, it's the root mean square. It's kind of average, but people will tell you why it's not. But it's basically like the median level of the mains voltage, which is an AC signal going up and down. The peak is about 320 volts and the capacitor will charge to the peak voltage basically. Looks like we have a resistor here which may be damaged. Not sure, maybe just something on it, yeah. And then here we have a switching transistor. So this switches, if you like, the coil on and off. So it's pulling current through this coil very rapidly. That generates a voltage in the secondary, which is over here. And then that voltage effectively will have a rectifier diode there. This looks like a MOSFET probably. Voltage reference, smoothing capacitor. So out of here comes out the low voltage. We have 2 diodes as well there, but that is probably a diode. These possibly have reverse voltage protection. I'll have to have a look why they're there. And that's basically what we have. This opto isolator, effectively part of the circuit, monitors the voltage on the output and controls the switching transistor. If it needs more output voltage, it switches on for longer periods of time. So that's basically how this works. The only thing we can't see is what's switching this. This could be a transistor or it could be something with more legs. That is actually a switching device and controller in one. But let's have a look on the other side. Well, here we have some chips. Okay. We know this is the mains input, this area. What I haven't tested for, and I'm going to do now before I start poking around, is whether this large capacitor has any voltage in it if it's charged up. Okay, so that's the first thing we need to check for safety. The capacitor in certain fault conditions can hold a high voltage for a long time, and if you touch it, it will hurt. Okay, so let's have a look. Well, there's practically no voltage, it's about 0.3 of a volt. Okay, so that's fine. I shouldn't be using these probes on the high voltage, by the way. I think these are only 30 volts or something. Doesn't say, but they're good sharp probes. Okay, so there's no dangerous voltage in this. I can touch this, it's not a problem. And if we look, it looks like there's some sort of just water damage. Can you see around here, like a ring of water, unless it was just some sort of glue that held this into the case. I was brought just the PCB. And this chip is on the high voltage side, so we have this big gap in the PCB here. This is the high voltage circuit, okay? and it drives the primary of the transformer. So the transformer is here, primary, secondary, okay? You can see it's there. When I say primary and secondary, you'll see there's 1, 2, 3, 4 pins here. There'll actually be 2 windings on this side. One is the primary that is being switched by the switching transistor, and the other one is another secondary that generates the power that this chip needs to keep running. So there'll be somewhere here probably a high value resistor or some in series. Could be these actually. What are they? 2204. Okay, so that's 220 and 4 more zeros. That is 2.2 meg. 2.2 meg. Looks like I've got yet another one. This, I'm pretty sure it is the startup. One end comes from this capacitor. Can you see it there? That's the positive end of the large capacitor. This is the negative end, and these are in series. 1, 2, 3. Looks like they're in series. Let's have a look. Let's go to continuity. Does this one connect to this one? Yeah. Does this one connect to this one? Yeah. And then this end here will power this chip initially. So when we switch on, this capacitor will charge to 320 volts DC. The high voltage will come down through these large value resistors, 2.2 mega ohms each. So that's effectively like 6.6 meg. That will come under here. I can't exactly see what's under here. Looks like it goes that way. Is this just a wire link? Yes. And then from here, this will provide initial power to the chip. So this will charge this capacitor and power this chip. The other end of this capacitor should go to ground, which is the negative end of the large capacitor. When I say ground, it's hot ground, okay? It's not a safety ground. Don't touch it, yeah? This is connected via the diodes and the bridge rectifier to the mains, live or neutral. Well, actually, both of them alternately 50 times a second, yeah? So that circuit is what powers this chip initially. This chip will have another power supply coming from the other secondary on this winding. I'd have to track it out to see where the switching transistor is, but one winding on here will also power this chip. And this chip drives the transistor, and that's what switches, okay? So the first thing we need to do to look at this is have a look for short circuits on the output. Make sure there aren't any, okay, shorts on the output. In fact, I can do that now. Don't see any shorts here, okay? And we need to have a look to see whether this circuit is in place, basically, and which of these is the primary. Let's have a look. So we have no connection there. I've gone to resistance range. Well, that's 0.4 of an ohm. Okay, that's a winding. This will probably read much the same, yeah. Hot ground. Reads 0.5. That kind of reads open. 0.2. And kind of reads open. Okay, so that's a little bit strange. I would have expected to see a resistance across this winding, and I don't. And I see a connection between these two, but not to ground. I see a connection from this one to ground. You wouldn't expect to see a connection from the other winding to ground. but I do. So that one there and that one there go to ground. Okay, this is not reading like I would expect it to read. I'll draw out on paper what I think we should have, and then we'll have to investigate this a little bit to see what we actually do have. So without looking up any data sheets or seeing what this chip is or anything else, we can work out, or we should be able to work out, basically what we have here. So we have effectively mains coming in via a fuse, via some inductors, the capacitor maybe across here, maybe across here, maybe across both, and that will go to our bridge rectifier. AC, AC, plus, minus, okay? Minus gives the hot ground. This is our reference point for all our measurements, but it's not a safety ground, okay? Plus goes to one end of the primary of the transformer, okay? And the other end of that will go to a MOSFET usually, and that will connect to hot ground. It may have a small value current sense resistor there. I haven't looked. It may not. And if it does, it'll be less than 1 ohm, maybe 0.1, 0.2, 0.5, whatever, yeah? This MOSFET will be driven by the controller chip. Quite probably with a resistor in it. I haven't looked again. But we'll have something like this, yeah? Pulse width modulator, okay? From the pulse width modulator will connect to hot ground. And then this has a supply, okay? And the supply will come via these 3 high value resistors that we can see. 2.2 meg each. 2M2, 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 okay? And this will either go via a rectifier diode to here, or it will go to here. We'll call this point here HT, plus HT, high tension. Yeah. And this here will probably go to there, plus HT. And we'll have a capacitor, we know we do have, because I've just found it, yeah, we'll have a capacitor from here, it goes to hot ground. Okay, so I've missed one other thing off here, and we need to put it in, and that's the big smoothing capacitor, the bulk capacitor as it's called, and that's also connected to hot ground. Okay, and this capacitor is this one. On our board, can I see the markings? Yeah, it's a 100 microfarads, 400 volt capacitor. Okay, this is a thing that can hold a nasty high voltage charge in certain fault conditions. So that's how this works. This is VCC. So when we plug in, as long as all this is okay, the bridge rectifier is okay, this charges to a high voltage. This MOSFET is switched off at the moment, so current can't flow through there. But current, a small amount, can flow through these high value resistors and charge this capacitor. Okay? And the capacitor charges up, and when it reaches a certain voltage, let's say 15 volts, this chip will switch on. And this will then start driving this transistor, switching on and off very rapidly, pulling current through here, and that generates the voltage in the secondary. Okay, this now goes to safety ground, but it's isolated from here, and this goes to out. Okay, we have some sort of current sensing setup, but that's what we have, okay? But in the way these things are always designed, this set of resistors can't provide enough current to keep this running. So once this starts, this is switching, the voltage in this capacitor starts to decrease because this requires more current than it can get this way, so it starts to discharge the capacitor. And when the voltage in the capacitor drops to say 9 volts, if nothing else happens to keep this running, this will switch off. Okay. And then depending on the chip, this will charge up again and it may switch back on, or it may stay switched off till you plug it back in. But as I said, something else needs to happen to keep it running, and the something else is where this other secondary comes in. So the other secondary goes from hot ground, okay, and it then feeds voltage back to here, and it does it via a diode, quite possibly a resistor, maybe another capacitor here and another resistor, but this is probably just a diode or a diode and resistor, and that will feed voltage also to here. Okay, so the idea is this starts switching, this starts running, it generates voltage into the output, it generates voltage into this winding, and this provides enough current to charge the capacitor back up, and this circuit can keep this capacitor charged so this can keep running. Yeah, and that's what we have. Now when I say that's what we have, that's what I would expect we have, but looking around this transformer, it doesn't seem to be the case, because I seem to have one end of each winding connecting to ground, when I'd only expect this one to be connected to ground. I wouldn't expect this one unless that was short, but if that is short, maybe this fuse is blown, so that's why effectively if I plugged it in, it's not blowing fuse, the guy says it is dead. Okay, so we could have a short here. There's got to be some reason why both of these read to ground, if that's what we have. The other thing is that from across these windings, they both read like the open circuit, and that also isn't correct unless I'm just measuring the wrong pins. So let's have a look again what we have around our transformer. Well, it's fairly clear to me at least that we have 4 pins, 1, 2, 3, 4, and we would expect one pin, this end of this winding, to go to hot ground, which is the negative end of the large capacitor, which, oh, to see down there, it's here. Okay, so we would expect hot ground to go to one end of one of the windings, the secondary on the high voltage side. It does go to there. That is the end of this winding. Okay, but if it goes to there, you would also expect it to go to the other end of the winding, through the winding, and read the low resistance, and it doesn't. That reads high, but it also reads here, and that we can clearly see is connected directly to ground. That one, maybe this pin and this pin are this winding, not the two, that one and that one. If that's the case, the other winding should go to the positive end of this capacitor. Okay, that end does. So does that end read to here? Yes, it does. So it looks like this is one winding and this is the other winding. This one being the primary, one end connecting to HT, and the other one being the secondary winding, this one end connecting to ground. So that reads a strange order of pins, but it reads how I would expect it to read. So if that's correct, I can see that this pin, actually the track goes to there. So that is the ground end of this winding. Okay, this should be the supply end, the positive end, and this should go via a diode to one pin on this chip. Let's have a look. Unless there's a resistor in there, of course. Well, yeah, it reads diode to there, and that's the pin that goes to these high value resistors. Yeah, so those would be the two supplies coming into here, so that looks correct. Yeah, then it's the other winding. One end goes to the positive end of the capacitor. Could be either because I'm reading the resistance of the winding, and the other end should go to the MOSFET, which is there. Okay, which is, let's see, where's the pins? Well, if that is a MOSFET, I can only see 2 pins, unless it's 3 and the third one is there. I'm going to have to scrape some of this gunge off it and see what we have. But let's just check. So from the positive of the large capacitor goes to that pin. Yeah, there's the winding, that's the pin. So that then you would think is the drain on our MOSFET. And the source will be one of these two. The other one will be the gate. Probably the one with a heavy track coming from it, and this should go to the negative. Yeah. So what I'm reading now, I'm reading from the positive end of this capacitor through this winding to here, and I'm reading from the negative end of the large capacitor, these points being connected to each other, to that pin. Yeah, and then the other one must go to the controller chip. Not necessarily directly, but we can have a look. That would be this pin. Well, it certainly goes off in this direction. Goes onto resistance range, just have a look. That's about 90k. 51 ohms, okay. Looks like that's probably it with a 50 ohm resistor. Yeah. There, 51 ohms. So this is pin, let's see, which is pin 1. Let's get the microscope. Yeah, this is pin 1 by the looks of it, a little mark there. And it's marked here like a little notch. So this is pin 1. So pin 3 is the one that the power comes in from the secondary winding, which is this circuit basically, and the high value resistors in series, you can see them there. That also comes down. This is the capacitor that gets charged that I was showing you on my little diagram. So that's that, and then the output of this chip through 50 ohms, which is this one, and that was like a 51 ohm resistor there. That's what's driving the MOSFET, okay? And the MOSFET is here. Yeah, and that's the gate. That seems to come this way. Possibly goes to the 51 ohm resistor. Yeah, that all looks like you would expect. So, without looking any data sheets up, we do know something about our power supply. Now, can we see what the chip is? I'll get it under the optical microscope and see if I can see it all. Well, they've tried to make it difficult to read. I've just rubbed at it with a cotton wool bud and some ISO propyl alcohol. So it looks like you have 17. Just read that top row, it's a bit awkward. (1710G1). Yeah, 1710G1, R5JPS and AB1508. None of those mean a great deal to me. So let's see if we can figure out what is wrong with this without having to find a datasheet for the chip. First thing then, is the fuse any good? Okay, so this is the fuse. And no, the fuse isn't good. Okay, so the fuse is blown, we can say that much. That's the first thing. Do we have any shorts across the main capacitor? So we know this is open circuit. Is there a short somewhere, either across the AC terminals of the bridge rectifier or a short circuit diode, or across the output? Let's have a look. So across the AC is easy. This is the two filter coils here. Yeah, one in the live, one in the neutral. So we could just measure across here. Now we have a short, okay? We'll see it here as well, this side. So we're reading a short on the AC side. How about on the DC side? That's across the main capacitor. No short there. So if we're seeing a short across here, it's either the bridge rectifier diodes or a capacitor somewhere here. Now these bridge rectifier diodes, I'll just show you how they're wired up in more detail now. So we have 4 diodes, and ours has 4 individual diodes, okay? And they're wired like this. That's plus. That's minus. And plus and minus are going to the large capacitor, okay? And there's no short there. This is AC, and we have a short across here, okay? So what's causing it? Well, here are the diodes. I can see the diodes. They're actually slightly buried in the gunk here, but you can see one is standing up and the other ones are there. So let's check the diodes. We'll do this in diode mode. I suspect these are okay, which is why I'm not seeing a short on the output of the large capacitor. Let's have a quick look. Well, that one reads okay. Those read just like open. This one reads like a diode. Yeah, that reads like a diode, and that reads like a diode. And both these ends are connected together, and that's the negative end of the capacitor. Okay, so those two are these ones. Okay. And the other two, well, again, one end is connected together. That's the positive end of the large capacitor. So if I put my red on the AC here, should read a diode, and that reads a diode. So the bridge rectifier reads okay, which kind of is what you would expect, because if there were shorts in here, you would see a short across the plus and minus as well. So what's short on this? Well, all we really have is a capacitor here. Okay. The inductor, this one here, well, one end of that goes to the fuse, and the other end of it is here. So let's see, what do we have? Well, we have live or neutral. Live, I'd say these are live. Going to our fuse, other end of the fuse is open. We have a direct short. We would have a direct short across live and neutral if this wasn't blown. Okay. So where is the short? Well, this thing looks like it's wired across the mains. This thing. What is that? I mean, that looks like an inductor. I don't see why that would be white. It's like we've got what looks like an inductor here. That doesn't make any sense. We also have this capacitor isn't there, it's on this side. Like so. Right, let's take the capacitor out. Oh! Oh! No, this isn't wired like that at all. This is 2 inductor coil windings. Yeah, I can see now one there, and I can see 2 more pins. So what we actually have, I can draw it now. We have fuse, inductor winding, which is that one, capacitor, inductor winding, okay, live neutral, another inductor winding, which is the big one, and then the bridge rectifier, okay, and we have a short across here. And unless something like has gone wrong inside there, like 2 windings are touching, it would seem that the capacitor is the most likely thing to be short because it's directly across the 2 terminals. And if we measure across the capacitor, it's short. Okay, let's remove that capacitor. Bit of braid. I put some flux, as you've noticed. Makes the braid work much better. Okay. Okay. Just need to get this glue off now. Looks like I have it, okay. And the capacitor is coming out. Okay. Is our capacitor short? Well, it doesn't look distressed, I'll say that much. Let's check it. No, it's not short. Do we still have a short across here? Yes. So it's somewhere else. Well, not much else left, is there really? There's only the 2 inductor windings. This one seems the most likely culprit because the windings are like on top of each other, whereas this one is like 2 separate bobbins. I can't really see how you could have a short inside that one. Okay, let's remove that one. If this has a short in it, this is really unusual, guys, because it's not common that this would happen at all. In fact, I doubt it somehow. I think I'm missing something somewhere with this. Missing the point, yeah? Let's have a look. Okay. See if we can lift these up. I think I've lifted the legs. Let's see if the short's still here. Well, I don't read the shorts across here anymore. Okay. But I do across here, so it must be this. See if it'll come out. It's out. Okay. Well, the short's gone. Put us under the microscope. Okay, so here is our device. Now I think we can see effectively that the insulation here is melted, I think, on this one to that one. Or somewhere in here. Probably here. I think that's where our short was. Or here, can you see this is like kind of like melted? Okay. Yeah, looks like it to me. Yeah, that looks like it to me. It looks like there's a short, or it's been arcing in there. Let me see if I get the focus for you guys. There, okay. That's what has caused the problem, down inside there. Okay, see it? It's kind of all stuck together with some sort of epoxy resin in here, yeah, this stuff. So I think if we just took this out of circuit and effectively just bridged the two pins in out together, so there's two separate windings here, you can see, I think it would probably work. I can have a quick look see if I have anything else that might do, but I'm not sure I do have. But without this in, I think if anything it might just cause a little bit of mains interference, but I don't think it'll cause that much of a problem, especially considering that there was another inductor bobbin anyway. Yeah. But let me have a quick look if I have anything like that. Okay, I've wired the fusing. I've put it along there. You can see I put some heat shrink on. We can just check it. See? Yeah, reads okay. Just before we find out if we've now repaired this, here is a quick word from the video sponsor. Let's plug this in on the current limiter and let's see what it does. There's an LED which lights up. Maybe that only lights up when you put a battery on, I'm not sure. So I'll connect my voltmeter across the output as well. I think that is the output, those two. No, there are 4 separate pins, so I'm not totally sure what the output is. And they're not connected together, okay. Well, we can plug this in and let's see what it does anyway. This video is sponsored by Solder Stick. Solder Stick make a range of connectors, and one of their products is this one. So these are solder stick connectors. They come in a variety of sizes, you can see in a handy pack. And these are used to make waterproof joints between wires. They can be used on the bench or in the field, and they're very simple to use. We just need to prepare the wires by stripping the insulation. We don't need to add any flux or solder. Just quite literally like so. Now we've prepared the wires, we can look at the solder stick connector. So this has two coloured bands. These are actually a waterproof adhesive, so these hold the joint together and weatherproof it. The metal band is a low melting point solder. So to use the connector, we simply insert the wires like so, and we heat. We can use hot air, or we can use a cigarette lighter or some other form of heat if we're on site, for example with automotive repair. But I'm on the workbench, so I will use hot air. First I will heat the solder to melt the solder. This will tin the wires. Okay, and then we can heat the glue. This is like a heat shrink sleeve, but with an addition of a waterproof glue. And there we have our connector. Okay. We simply now need to let this cool down. You can see the solder has melted and tinned the wires nicely in there. This is still flexible, but it'll form a very strong bond. I'm pulling very hard on that, as hard as I can, and it's not moving, okay? It's really soldered well together. In the video description, you will find a discount code for solder stick. Give these a try, guys. I can really recommend them. They are ideal for use in many situations. Bulb flashed and went off again. LED isn't lit. Yeah, we have voltage here. Okay. So we do have some voltage coming out of it. I'm not sure what it should be, to be quite honest, with the battery not attached. So I'll just have to give this back to the guy. I haven't got the housing, I haven't got the drill, but we've got some voltage coming out of it, so I suspect it may well be okay now. I'll let you know, guys, if it comes back again. In fact, you'll see it if it comes back again. But for now, I think we can call that fixed. And I know I could have fixed that quicker if I just checked straight away, fuse, and then found the short. But hey, you know, I'm trying to teach some of you guys as well, and I hope you learned something. Slightly long way round. It's not really about how fast you can do this when you're learning. It's just a matter about learning, yeah? And we got a result. Okay, so I look forward to seeing you all soon on another Learning Electronics Repair video. Ciao for now, guys.